Hi everyone, welcome to this webinar. The webinar title is 3D Modeling Masterclass from Geometry Creation to Results using Slide 3. My name is Sina Javankhoshdel. I am the Senior Manager of the Limit Equilibrium team at Rock Science, and I'm hosting this webinar today. We are Rock Science. We are a global leader in developing innovative 2D and 3D engineering software. The company was founded in 1996 at University of Toronto, and we developed so many programs for different applications. And now we are the industry lead for software solutions, exceptional customer service, and unparalleled technical expertise that engineers worldwide can trust and rely on. We have 20 programs, as you can see here, including Slide2, Slide3, RS2, RS3, and 2 new programs, RS Seismic, which used to be Deep Soil, and another new program under the umbrella of Slide and Limit Equilibrium team, which is RS Wall. This is the software ecosystem at Rock Science. You can see as all these programs are being developed in-house in Toronto, different teams work together to make integration between programs. For example, Slide3, which is the focus of today's webinar, is integrated with RS5, Rocket Slope 3, RS3, and Slide2. And other integrations as well, and we keep improving this ecosystem by adding more programs to it and more integration between the programs. Today in this webinar, I'm going to talk about 2 of these programs, actually 3, including RS3, but the main ones would be a Slide3, which is the main focus of the webinar, and a little bit of a Slide2, which is the 2D version of the Slide3 software. So to show you what we have in this webinar today, it's a very comprehensive webinar. I'll explain what's going to happen in the webinar. We'll start with the geometry creation review. Then I'll talk a little bit about material models in the slide, groundwater options that we have, search methods. We do a couple of demos, and I'll talk about the results interpretation as well, and also the integration between a Slide3 and a Slide2 software. This webinar is basically a continuous to the previous webinar that I did with Dr. Sina Moallemi 2 years ago, which was called Masterclass on 3D model creation with the Slide3 and RS3. That webinar was focused only on creating the models and creating the 3D geometry. Now we want to quickly review what we mentioned in that webinar and then move on to see what happens after you created your 3D geometry. So let's get to that. Okay, let's start with the 3D geometry creation. Slide3 and RS3 share the same geometry tools. So basically, you can create geometry from scratch. You can bring Slide2 models into Slide3. You can like draw polylines and create 3D geometry. So there are different options that in this section I'm going to review it. Keep in mind, Slide3 and RS3, they don't need a third-party software for geometry creation, and all the CAD tools and geometry creation tools are implemented in the program. So let's quickly review those. So basically, this is coming from our previous webinar, so I'll quickly review these. 3D geometry creation goal and procedure. Basically, there are a couple of steps that you need to do when you create your geometry. If you want to start from scratch, you can import your geometries. The main thing in geometries is the number of triangulations, so surface triangulation to create the geometry. So you need to verify and confirm this number of triangulation, which should not be like too large, like 2 million, 3 million. These numbers are too big. Then you start cleaning up and repair the problematic geometries, and you find the defects and fix those in the program. Then you define an external geometry, which is the boundary outside of your geometry, and then you intersect the clean geometries with the external geometry. So this is a simple part. It's called divide all geometry. And at the end, you do another level of cleanup, which is for the divided geometries and collapse small volumes. What is the goal here? The goal is to achieve divided clean geometries with the minimum number of entities possible. So that's a goal when you create a 3D geometry. Keep in mind, slide 3 cares less regarding like the bad geometries compared to RS3. In RS3, your geometry needs to be clean enough to be able to mesh the model and compute and converge the model. But in a slide 3, as long as you are able to create a 3D model, you can compute it with much less problems. Now, we talked about how cleanup part. So there are 8 steps that you can watch our webinar, previous webinar on YouTube channel of Rock Science. We talked about these in more depth, but there are 8 steps, which includes retriangulate geometries. If you want to repair with one-click repair, you can do that. If you see a lot of non-manifold issues, you do ungroup non-manifold, or if you see separate geometries, you do ungroup disjoint. If you have volumes, always you need to do form closed triangulations, and after, if none of these work, you have to go to the next step, which are steps 7 and 8. For geometries, the geometry repair to remove part of the geometry, you need to increase the resolution of your triangulation. For some cases, it might work. And at the end, if nothing works, you need to take the geometry in a separate project and do a divide all geometry. So these are like very hard to understand on this page. So let's go one by one quickly. And see what I mean. So basically, this is, if you look at this geometry, if you look at the triangulation, surface triangulation, the triangulation is very dense. So, and if you go to the repair tool option that we have, you see a lot of issues. With one click of retriangulation, which is recommended for every single geometry that you import to slide, you need to retriangulate and fix these issues. You can see how the triangulation is smoother and a little bit coarser than the previous one, and with the same size and much less issues. Then for models that they don't have so many issues, like these numbers are small, you can just with one click on the repair here, repair option here, you fix the issues, and that would be it. You can see these issues will be 0. So the geometry is repaired. I talked about ungroup non-manifold and ungroup disjoint. So I prepared a video here that I'm gonna play. This is a geometry. It has so many issues. So we look at the repair dialog first. You can see how many issues we have. And you have so many ungroup non-manifold problems. So, and also the triangulation is not nice. So first step, we retriangulate always. So this is the first step, and you can see the triangulation is very nice. Now we go to the repair option again. It's still some issues, especially non-manifold issues. We go to surfaces, surface triangulation tools, and ungroup non-manifold. Once you click on that, you can see there are several pieces that you don't even see them. You can just change them to construction row and discard them, basically delete them. Again, we go to the repair tool and see if we have so many issues. Still, there are some issues, but let's click on repair and see what happens. It seems that it fixed some of the issues. We can go back, do ungroup non-manifold again, and there is a piece there left. Discard it, and you go to the repair tool and repair again. This is a quick process you see here, but literally like more than 60% of the time you can do it. So that's for ungroup non-manifold and ungroup disjoint. So we look at the repair dialog. If we have these kind of problems, we use these options. The next one would be this one. So if you have ungroup disjoint, like if you see your geometry, it has several separate pieces that these are visually can be seen. First, we retriangulate always, regardless of the geometry, always retriangulate to make sure that the triangulation is meeting the software standard. Once the retriangulation is done, we have to take care of these disjointed pieces. So this is done. Now we go and the repair dialog to see what kind of issues we have. We can see that there are so many issues. Most of them is because of those disjointed parts. So we go to ungroup non-manifold or ungroup disjoint, and you can see how many pieces there are. If there are so many pieces, you can always do a query in a slide 3. For example, here we want the pieces larger than 50,000 in size, and the rest you can just select them, change them to construction, and discard them. And you are left with 3 big pieces. Now for the biggest one, let's repair it again. You look at the repair dialog. There are not so many issues. And now you can see that it is fixing the problems with one-click repair. And one more time, it is completely clean. So this is for geometries with these several disjointed pieces. Next, if we have volumes, always it is recommended to do form closed triangulation. So if we go to the repair tools, for example, look at how many issues you have, and if you try to fix them, part of your geometry will be gone. So we don't recommend that. We do an undo, and then the first step would be to ungroup them. So now you can see that there are 2 big volumes and 1 small one, which can't be even seen. We discard that. Then when you have 2 volumes, we do form closed triangulation to make sure that they are intact volumes. We hide them, we remove these small pieces again. And now we need to repair this. Sometimes, as I showed before, you can easily repair these geometries. Let's see if it is repairable. You can see still part of my geometry is gone. It seems that at that location, we require to have more resolution, better quality resolution. That's why sometimes this is the same geometry. You can retriangulate your geometry with a higher resolution. So if we look at the surface mesh, it is not that dense, but we can go to the retriangulate option, use the custom option, increase the resolution, and now it's very dense. Let's repair this one more time. This time we don't do repair all. We have an option called repair selected. We select the issues and then repair them. And in this case, we have a high resolution, so you have more accuracy and the software can repair it easier. You can see that now all those issues are gone without changing your geometry shape. So that's increasing resolution will help, but keep in mind, you have to retriangulate again to make sure that you don't have such dense geometries and your geometry, your triangulation would have a coarser triangulation. So, and the second volume, you can easily repair it, and it's all repaired. And the last option that we have, if none of these work, there is one more option. You can always export your geometry to a new project and retriangulate first, do ungroup non-manifold, ungroup disjoint, discard the small pieces, and then put a volume around your model and do the divide all geometry. Again, these all with more details are in the webinar that we had, and it's on Rock Science's YouTube channel. You can watch that webinar. It is more comprehensive. This is just a review. So here we discard the small volumes and just keep the big ones. You can see that these are the small ones. Then let's look at the prepare menu one more time. After doing, because these are all volumes, we do form closed triangulations. As I said, for volumes, we do form closed triangulation. And let's try and repair one more time. If I repair this geometry, you can see here that part of my geometry will be gone again. See how that part was removed? So we undo. Now we tried every step, none of them worked. We just create a big volume, big box around this and do a divide all. Why we do that? Divide all geometry has its own repair tools inside it. So it is recommended to do all these steps and then do the divide all geometry to make sure that your geometries are repaired. It is a very quick process, and you can see that now every geometry, every piece of geometry is divided. It means that it is repaired based on the standards of the Slide3 software. Now you can export it and take it to your original project. So this was a quick overview of the process that we recommend to repair geometries. The way that today's webinar works, I go back and forth with my live demos to the presentation. So I talk a little bit about some features in Slide3, go back to my demo, apply those, come back to my presentation to make sure that it is interactive enough. So let's go to the Slide3 software. So this one is this is Slide3. I want to create a dam model by importing the geometries for this model. These are the geology pieces of the dam. You can see that every piece is here. These are just volumes. As I mentioned, you need to check the triangulations. When you're done, click on done, and these pieces are in. There are several pieces here. If I look at all the geometry pieces at the same time and go to the repair menu, normally we recommend to do like a smaller groups, but since I knew in advance that this geometry is not that bad, I looked at all the pieces again. So you can see that here we only have one self-intersection and the rest of the issues are near degenerated and near folding. When you have such a case, it is recommended just not to repair it. You don't have to repair it because the software is fine in terms of dividing the pieces. So what I'll do, I just create a box around my model, which will be my external box, and then I'll go to geometry, 3D Boolean, divide all geometry. Divide all geometry, as I mentioned, is going to intersect the geometry pieces that they are not part of the external volume with the external volume. So basically to create the geology in my model. But there are different options here. You don't need to do anything, just use the default. And the software is going to intersect the pieces with that they're not part of external with my external geometry. and at the same time apply some repair tools to the geometry pieces that they have like minor issues as well. You can see here and in the previous examples that once you get familiar with geometry creation process in Slide 3 and RS3, you can easily create complex models. The divide all is done, and this is the external box around my model. I don't need it anymore. I can just change it to construction and discard it. That's it. Now my model is created. Very simple. Every piece, there is a lock in front of it. It means that it is already divided. And if we go to the 2D view, this is the divided part of my geometry. And I change this, like move this slider, and you can see different part of my geometry. Now, once the geometry is created, the next step would be to apply your material properties. I haven't defined any material properties in this model. I'm going to go back to my presentation, and let's quickly talk about material models in Slide 3. So there are 17 material model types in Slide 3. In this slide, I show the ones that we have in like a Slide 2, a Slide 3, or in both programs. Most of them are available in both programs, so you can see how seamlessly is integrated the Slide 3 with the Slide 2. Some of them that we have in the Slide 2, we don't have it in the Slide 3. Some of them we don't need it, like no strength material. We have other options in the Slide 3, or some of them they are not applicable in the 3D model. But you can see the comprehensive range of material models from isotropic materials, such as the typical one, more Coulomb, C5 function, different functions, to anisotropic material models like generalized anisotropic, strength, different options. These are two of the examples. For example, generalized anisotropic option, you can define your base model, you can define your beddings, you can have different beddings, you can define your bedding using dip and dip direction, or you can even define your anisotropic model by importing a surface and assign it as an anisotropic surface. So that's for anisotropic. For isotropic models, one of the typical ones is shear normal, which if you have data from your tests, you can define shear stress versus normal stress and import it to the program. So basically, create this failure envelope inside the program. This is one of the typical ones. The other thing that we have in the Slide 3 and also in the Slide 2 is a block model. Block model is the data that a lot of mining companies and a lot of geological programs they export. These are in the format of CSV files. So basically you have X, Y, Z value. In a Slide 3 and RS3 recently, you are able to define your properties at the block level. If you don't have your external geometry, you can create your external geometry only with your block data. So this option is available in Slide 3 and RS3. If you have your external boundary and external geometry, you can just project your block model data on top of the external geometry. So both of them are available, and the software, when it does the computation, it considers the block data. And if you take a 2D section to Slide 2, you can see the block data in a Slide 2 as well. Now, let's go back to my model and see what we have in terms of material models. In this model, I've already assigned the material properties. I just wanted to show you, for example, for a typical dam, what material types you can define. For example, for filter, foundation, fill, you can just define the typical more Coulomb. For example, for the shell material, I use power curve, which is another material for dams. For the core and for the rock fill, you can just go here. I define functions for them. One is just a bilinear function for the core. The other one is a nonlinear function using the shear normal option. So you can mix and match different options and define your material properties in Slide 3. And this is the long list of the material types that we have. Recently, we added 2 different material types. One is similar to shear normal function, but it is for the undrained versus vertical stress function. And the other one is for the CNI rock mass function. So these are 2 new ones that we added to slide 3. To assign the properties, it's very simple. You pick the material type from the left and assign it to the 2D section on the right, and move this slider to make sure that for every section the material property is assigned. You can see that these are filter, rock fill, shell, fill, and core. So materials are assigned. Once you define the material properties and assign them, then we go to the next option. Let's see what we have in terms of groundwater in slide 3. So this webinar, my goal is to have like an overall overview of different options that you can apply to different models. So in terms of groundwater options in slide 3, we have water surface, RU coefficient, water grid. Also, you can have some advanced options like rapid drawdown and calculate excess pore water pressure in the model. Slide 3 does not have the seepage engine, finite element seepage engine, similar to slide 2, but you can, since slide 3 and RS3 they share the same geometry, you can just import the slide 3D models into RS3 and apply boundary conditions and do the seepage analysis. Let's see how that one works. So this is RS3. If you go to the file, import a slide 3 project, and we go to the like folder that I have defined these materials, for example, and this is a slide 3 project being imported into RS3. At the beginning, it asks you, do you want to apply restraints? I don't want it because I'm not going to do slope stability. I'm going to do only seepage analysis. You can generate mesh as well. You don't have to. You can generate the mesh later. And the model is imported directly into RS3. So this is the seamless integration between a slide RS3 and a slide 3. Now, you can go to the project setting of RS3 software. You can define different stages. You can go to the groundwater, do a steady state analysis or transient analysis. The reason that I define stages because I want to do a transient analysis. For example, I want to do 2 days, 5 days, and 10 days. Let's say this is a drawdown case, and we reduce the water level in different stages. Once you define that, in RS3, the stages are added, and you just need to go to the groundwater tab, define your boundary conditions, and then apply to your model, which I did in advance. So if I go to the boundary conditions that I define, I have a total head of 57 meters as an initial condition and the steady state condition. And also I have like seepage option as well. So there are different options that you can add. For example, if you want to add the drawdown case, you can define the transient boundary condition, as I mentioned here, and go and define the transient boundary condition and stages in the groundwater tab. So once you define the boundary conditions, then you can mesh your model. We have the new hybrid mesh option at RS3 as well, and you can refine your mesh, and then you can look at the results. So for the results of seepage analysis, you can just go to the seepage menu and look at the total pore water pressure. This is the total pore water pressure. You can look at the total head as well, and this is the total head in my model. So this is the C page in RS3. Now you can go on to export pore water pressure to slide 3. So basically you can export the data from a RS3 and take it to slide 3, which I did for this model. And if you look at this grid, if I go to the add pore water pressure grid, these are the grids that I imported and I read from RS3. So you can just go to import pore water pressure, and you can see that this is the pore water pressure data coming from RS3 to slide 3. Also, I have a ponded water in this model as well. So I define the surface and assign the water table to it. Keep in mind, you have to be careful that what option you apply to your soil parameters. For this specific example, I wanted the pore pressure for each material to be calculated based on the seepage analysis that I was done and calculated the pore water pressure in RS3. You can see that you have two options here, water table or water grid. We apply the water grid. So the only job that this water table does in this model is to add the ponded water in slide 3. So pore pressure is coming from RS3 and ponded water is being calculated based on this water table that I defined. Now, the water is defined in slide 3 as well. And next, we go to the next step. So we define the material properties, we define our pore water pressure. Now we have to set up your search methods. We have two different types of search in slide 3, classic search and intelligent search. Let's start with classic search. In classic search menu, you have different slip surface shapes. Unlike other like 3D programs, slide 3 has different geometry for the surface shape. Keep in mind, slide 3 is the standalone program in the market that gives you the most accurate results. I can prove it like with examples, but there is no competition for slide 3 because of this part that I'm explaining. So the shape of the slip surfaces, the way that we search for the slip surfaces is unique to a slide and is unique to the rock science team, and no one else has this. So we have different surface shapes: spherical, ellipsoidal, spline, which is more flexible shape, multiplanar, and wedge. These are surface shapes. Once you calculate your global failure surface, you have something else as well. This is developed in-house. You can look at this paper by Ma et al. 2022. We talked about it in that paper. Basically, we create a control net from your surface and start playing with it. We change any shape, a sphere, ellipsoid, to a spline, which we added later in addition to a sphere and ellipsoid, and a control net, and then start playing with the control net. How do we do that? We do different things. These are just local optimization. So on top of your global optimization, you have a local optimization as well. We modify the frame elevation, we do bubble gum stretching, we do shift and scale, different things to locally optimize the failure surface to get a better factor of safety. Then, for some cases, like traditional in limit equilibrium analysis, everybody is looking for a global minimum, and good luck with that, because especially in 3D search, a lot of people always get trapped in local minimums and they don't reach the global minimum. That's why we came up with a new method called multimodal optimization, that we search for local minimums. Obviously, the global minimum is among those local minimums. So we do more steps. And if you look at the slide 3 or slide 2 results, recently we just don't report one failure surface, one factor of safety. We report a bunch of them, which include global and local failure surfaces. For example, this is an open pit mine example with the yellow material, which is the weak material, and multimodal optimization captures 3 very close values of factor of safety, but totally different slip surfaces. And that's the beauty of multimodal optimization. Again, unique to Slide 2 and Slide 3. Before we go to intelligent search, let's go back to our model. So for this model, I did a couple of things. I want to show you why I'm claiming that the Slide 3 results are the most accurate. So for this example, what I did in terms of surface search options, I did a typical that people do in other programs as well: ellipsoid or a sphere failure surface, cuckoo search, and I turned off the surface altering, which is a local optimization. I want to show you how important this option is. And this is the only red warning that we have in Slide 3, because local optimization is 3D modeling is very important. But I turned it off. Let's look at the results. This is my failure surface, which obviously it is ellipsoid because I did not apply any local failure, any local optimization to it. It must stay ellipsoid. Factor of safety Spencer is 1.74, and yeah, this is the factor of safety. Then what I did, I went one step further, and this time I turned on the local optimization. I didn't do anything else. I just turned on surface altering optimization. Look at the shape of failure surface. It is nicer. It is not just ellipsoid. It is locally optimized. Factor of safety dropped to 1.67. So even it went lower. This is a simple model. You don't expect to have a large difference between the factor of safety, but it's still with surface altering, shape changed, and also factor of safety goes lower. If you want to look at a couple of things in terms of search, you can go to show all surfaces and look at all surfaces that we did to search for this critical slip surface. Similar to Slide 2, you can add filters if you want. For example, show surfaces with a specific range of factor of safety. The other thing that we have, you can just turn this one off. You can look at the contours for your critical slip surface. For example, you can look at the pore pressure came from RS3. You can look at the base cohesion, see what material this slip surface goes through. Different options that we have. We have another option called safety map, which shows you based on the calculated factor of safety, what is the critical region. You can see that there is an orange region on the other side of this slip surface as well, on the side of the slope as well. But this is the most critical region. Then after this, I went one more step as well, and I changed to particle swarm multiple, which is the multimodal option, and I ran MMO. Factor of safety dropped a little bit more to 1.66. As I said, this is not a complex model. I'll show you the differences when you have a more complex model. So from no surface altering optimization to just cuckoo search and surface altering, and then multimodal, you can see that how factor of safety changed. If I zoom in, you can see factor of safety of 1.66 and 1.78 and 1.82. These numbers are close with totally different failure surfaces. So multimodal optimization gives you all these. So this was for the simple dam model. We didn't stop here. We went further to an advanced technique to search for the critical slip surface. So far, we just randomly throw slip surfaces in the model and try to find the critical slip surface. But intelligent search was a revolution, basically, in terms of searching for the critical slip surface. We said, okay, do not do random search like other search techniques. Let's start with analyzing your model and see where you have like a steeper slope, where you have more critical condition. Then we generate some preliminary solution, some initial slip surfaces, a lot of them. Then we identify the region of interest. Based on these preliminary solutions, we find out what regions can be more critical. We haven't started searching yet. We're just analyzing our model. We just see where can be more critical. Then we do clustering and focus on specific regions, a lot of them, and search closely in those regions as well. So we start analyzing the model, and then we come up with a solution to search in more depth in specific regions. This is the intelligent way of searching for the critical strip surface, and this is the cutting edge technology that we have in slide 3 and no one else has it. So this is the clustering. These points that you see, these are strip surfaces that we are trying to search in those regions, and they converge to a specific solution. One of the advantages of intelligent search is the coverage. You can see how we cover the entire model. This is the 4 kilometer by 4 kilometer model. It's not a small model. And see how these particles, they can cover the entire model. So let's go to a more complex model and create that one. So it's a big open pit mine. And I have these geometries, including the external geometry, the triangulation surfaces is good as well. This is like original geometry. So if you look at all the issues that these geometry, they might have except the original, the external, there are so many issues. So it's not as easy as the previous one. So I repaired group by group and divided separately. So it's a very complex model, but I followed the same process that I showed you previously in the presentation. So you can see that it's trying to read all these issues in the model. This is a typical model that we receive from our customers, and look at the number of issues. So for this, you have to pick a group, like AA group here that I have, repair them, divide them with your external geometry, and then go to the next group. So if you divide all of them, I repaired and divided all of them, you can see that these geometries, they have a lock in front of them and they are already divided. So if I look at the 2D section, you can see that this is the divided model. Next, for this model, since it is a mine, and in a lot of mining problems, we have different material types related to rock and isotropic material types. For every single one of them, we have a base model, and we have a bedding model, and also we have an isotropic model. So you can see that it doesn't matter how many number of bedding planes that you want to define. I use a base material and the bedding material and deep and deep direction for this example. Then I use this 2D tool to apply these isotropic material types to my model. Now, for the sake of this example, I ran Yambu model to calculate factor of safety. Step 1, as I did before, I did particle swarm this time, single particle swarm with a spline surface, more flexible surface, without surface altering. So I got the factor of safety of 1.495, or around 1.5. And the shape should be very close, like this is a spline, more flexible. If I picked ellipsoid, it should have been more closer to ellipsoid. Then from 1.5, it dropped to 1.34 by just applying turning on the surface altering optimization option. And you can see that factor of safety dropped. And the final one is the intelligent search. So from 1.34 to 1.27, and 1.27 compared to 1.5, which was for the non-surface altering model. You can see different steep surfaces, 1.27, 128 and 1.5. So different failure surfaces, different factors of safeties. For this model, if we go back, I want to show you the safety map. Look at the safety map. Look at the coverage around the corners of the model. It shows this region is a critical region. Then when we go to PSO with surface altering, the coverage is literally the same. It's just the critical slip surface was more locally optimized. And the last one, this one is very interesting. If you turn on the safety map, look at the coverage of the intelligence search on the corners, and it identified actually more critical regions. So what method should we use? That's a big question. Intelligent search is designed for big models because a lot of times, for example, people run this and say, okay, this region looks green as well. Should I run, put a box around this region and run a slips like search here? Or if you identify more regions, you put boxes and search for those regions. You don't have to do that for intelligent search. Intelligent search automatically identifies all the regions for you. So for big models, like these landslides, these open pit ones, or big, large civil project models, intelligent search is the best tool. You can even put a box and it will be more accurate. And if you look at like surfaces, the number of surfaces that we search is 15,000. For other methods, we only do 800. So that's a difference between intelligent search and other surfaces, and the speed is not that slow. So it is fast and very accurate. So you can see all the surfaces that we used to search for your model, and look at them, how it covers everywhere. The other thing that I wanted to show you in this model is how we identify the anisotropy in the model. So you can always go to this contour option. The contour option in slide 3 identifies the materials that these slip surfaces they go through. They identify the stresses at the base of the columns, the column depth, the anisotropy. All these they can be identified using these contours. For example, if I look at the base cohesion, you can see that it's 0. So it captures the anisotropy of my biggest material. So if I go to that material and look at the bedding, like the cohesion, sorry, is 32, not 0. It's 32, and you can see that it's blue. So the whole thing is blue. It captures the entire anisotropy bedding of my material. And that's the beauty how we do the search. If you just do ellipsoid only without local optimization, there is no way that you capture this. This is about the contour as well. Also, we have a column viewer in slide 3 that all the columns that we used to search, you can see material info and also the properties of each column. So this is so far so good, ideal. How do I confirm my results? Like that's something that we always recommend our users to do, and we use RS3. Like we use a different method to confirm the result of limit equilibrium. So for the, let's go back to the model that we have a dam, and let's look at the factor of safety that we got in RS3. So in RS3, we not only ran the seepage analysis, also we ran the slope stability analysis as well. So the factor of safety that we got from RS3 is 1.6, and this is the critical slip surface. If I go back to my dam model, you can see that factor of safety that I got is 1.66. very close and very similar, like failure region and a slip surface. So you can see how limit equilibrium and the slide 3 can capture the failure surface. How do I confirm this? Like you cannot do this. You cannot confirm the limit equilibrium results with finite element unless you use a good search method in the limit equilibrium analysis. And in that case, you can confirm with the finite element analysis. Now, let's do one more thing. I ran the intelligence search. It got a similar factor of safety for this model. Let me go back to my presentation first. In slide 3, we have an engine implemented, which is the Slide2 engine. So if you have the Slide2 license, you can add as many sections as you want in a slide 3 and carry out slope stability analysis and look at the 2D results. So let's go back to the DAM model. If we go to 2D section creator, you can see that there is an option to add, I can do it here. Let me delete these sections. We have an option to add sections, 2D sections in the middle of every failure surface. Since we do multimodal or intelligent search, you have different slip surfaces. So you click on add, the software automatically adds sections in the middle of the 3D failure surfaces. Keep in mind, if you want to compare 2D results with your 3D results, your section should go through the middle of your 3D failure surface. So that's what we do. We added an option for it. So I created these sections in advance, these 3 sections in the middle of 3 slip surfaces. Now we can either compute here because there is a Slide2 engine here, or we can go to a Slide2 modeler, open these, and compute them. You can bring even this 3D slip surfaces here as well. And these are pore water pressure grids that they came from Slide3. These are the ones that was computed in RS3. So you can see how our programs read information from each other. So you can just compute this one and then look at the failure surfaces and look at the factor of safety. So there are 3 different cases that we can compute and then look at the result. If I go to the results of slide 2, let me grab the results here. And let's turn off the symbols here. So this is the critical slip surface for this model. And the factor of safety, this is Yambu, this is the Spencer. I brought the Spencer section. So you can expect that the Spencer results are closer to like the 3D ones. And second one is almost done. Keep in mind, again, if I go back to the slide 3 file, the middle one, since it is the full 3D failure surface, can capture the failure better compared to these 2 small ones on the corner, because in 2D, you can, your assumption is that this material is infinite. So if you look at the corner failure surfaces, they don't match the 3D results, but the center one, since it is a more 3D shape, the 2D results would match the 3D results better. So second one is done as well, and you can see how the slip surfaces they match. Look at this, literally on top of each other. So if you make a proper section, the results of 2D and 3D will match as well. Thank you very much, everyone. We are at the end of our time. I hope that you enjoyed this webinar, and see you soon.